Welcome back, welcome back, welcome back. As we're approaching the end of the chapter, it was only a matter of time before we had to talk about the fields in matter and how to formalize the tensors for the matter fields. This question will turn into something very painful as far as execution of tedious work, but in terms of setup wise for the first few parts, it isn't too bad. I guess we just gotta jump in now. The statement A starts out with construct a tensor d mu nu out of D and H, the auxiliary fields. Use it to express Maxwell's equations inside matter in terms of the free current density J mu nu. B. Construct the dual tensor H mu nu. C. Minkowski proposed the relativistic constitutive relations for linear media. D mu nu times eta nu is equal to c squared epsilon f mu nu eta nu. And of course, we have one with the dual tensors, except for the constants turn out to be 1 over mu, which we saw that before with how the auxiliary fields are put together with their relationships. So here, epsilon and mu are the proper permittivity and permeability respectively, and eta mu is the floor velocity of the material. Show that Minkowski's formula reproduces equations 4.32 and 6.31 when the material is at rest. Finally, part D, work out formulas relating D and H to E and B for a medium moving at ordinary velocity u. And this is where things get messy and tricky, but A, B, and C should be a good background and formally setting things up. So without further ado, we'll dive in. All right, so for part A, we saw how we could finagle the components and the construction of the electromagnetic field tensor. We could also do a clever trick of seeing how E moves to the displacement field and B moves to the auxiliary field within how they're related. So if we look at the auxiliary field relational equations, we see that D is equal to epsilon, not E plus P. We're not really worried about this polarization term because we're worried about how D and E relate only. And we see that E goes like 1 over epsilon not D. Similarly, H compared to B goes like mu naught times H. We could clean this up a little bit if we divide both of these by mu naught, mu naught, get that off of H. And then if we do that for the D term, we see that it gets 1 over mu naught epsilon naught, which turns to C naught, or C squared, excuse me. And then we could substitute these little relations into the electromagnetic field tensor, and we end up with something very similar. Again, anti-symmetric as we expected. This used to be the E over C's. This used to be the negative E over C's, and then these were the B field components. So pretty consistent. And the same tactical switch like that will be used for the dual tensor in due time. Now let's go check out the equations. All right, so for Maxwell's equations, we want to evaluate the gradient 4 vector acting for mu between 0 to 3, okay? So if we want to sum over the nu for mu equals 0, this is the expansion that we have, okay? So here is the compact form, the expanded form, and we see how we have to write it out. I'm going to be lazy later on and just use the compact form, but here's how we read it across. So now we just have to read off the 0 components. So 0, 0, 0, 1, 0, 2, 0, 3, that's all the first row stuff. And as you see, our first term is 0, then we have CDX, CDY, CDZ. And if we factor out a C, we look like we have partial X on X, Y and Y, ZZ, so it looks like a gradient, or excuse me, a divergence. Oh, excuse me. Which is equal to C times the divergence of D,
which we know is equal to rho f, so that's equal to the 0th component of JF, the free current density. Now, if we do the same thing for the mu equal 1, or the x spatial direction, we see we get a nice little cancellation, a 0, hz, hy, negative. This looks like with the negative and all the partials, we get a time derivative here from the 0th component, and then we get two spatials. Notice that y and z are opposite with the minus sign, y, z. So that looks like our curl component, and it's the curl of h. So this has to be, based on one of the equations, this has to be JF in the x direction, if we look at the second inhomogeneous equation. That being said, if we did this for the mu equal 2 and 3, or the y and z component, we would get the other two components, and we could reconstitute this. Thus, if J mu f is equal to C rho f and the current density vector JF, then we show that the gradient operating on this new tensor here is actually equal to the free current 4 vector. So we proved what we needed to, and then we see that meanwhile the homogeneous Maxwell's equations, they remain unchanged, and hence we see that the gradient 4 vector acting on the field gives us a 0. So everything looks to be just running smooth so far. Now we gotta figure out what to do with the ladder. All right. Okay, so now that we're done with part A, we see that in part B, we just do the, we know from F to G, there was a rule in order to switch the coordinates. Now we modify that rule for D to H, and we see that we get a quick, easy, same antisymmetric tensor. Instead of how we had for G, the B's were on the outside rows and columns. Now we see that H's are on the outside. So everything's looking good so far. C, however, we stated that if the material is at rest, then the proper velocity 4 vector would just read negative C 0, 0, 0, and the sum over V would collapse to just the sum over nu collapses to just a single term. Since all of these are multiplying by 0, it doesn't matter. The 0th term here, so nu equals 0, is the only one that matters. So here we have the tensor d mu 0. Then we have eta 0 is equal to c squared epsilon f mu 0. So we see that the etas cancel on both sides, so we're good there. And then we see what's going on. The 0th component in this category here leads us to the d vector. Because we look at this is our row, this is our column, this is the 0th column. So of course with the negative summation over all of the mu's running from 0, 1, 2, 3. So we're looking at the first column and all entries in that first column. That creates the d vector. This creates a negative e over c, and we see we get a nice cancellation. This c canceled with this c, this negative c canceled with that negative c, and sure enough, we reproduce d equal epsilon e. Although technically this cancellation of this shouldn't really happen this way. You should plug in and multiply all points across. So that's just kind of lazy work. But nonetheless, we do reproduce the result we need to. Similarly, on the dual tensor, we have h mu at 0, and we do the same stuff. This time, we reproduce exactly what we need, just with the negative sign to cancel. And we see that we do recover equation 6.31. So everything is turning out really well. And then now all that's left to do is find out how to deal with finding the fields in terms of E, B, and the ordinary velocity U. And that's what the rest of this question is dedicated to. So let's dive in. In part D, we had, in general, if the proper velocity is given by gamma into the vector of negative c, u,
for some mu equals 0. Okay, let's see what we need to write out then. Here then, if we just have mu equals 0, then we see what this component will do, or what we'll get for this component. And then, of course, the idea is that we do mu equals 0, 1, 2, and 3, or mu equals 0 and 1, and try to extrapolate from them. But let's see what we do from the D tensor, plugging in for some eta proper velocity vector that we don't have a 0 frame in. So if we plug in the zeros, we see that we now have to sum over the news. So we get 0, 0, 0, 0, 1, 1, 2, 2, 3, 3, and then we can plug in all the components. Clearly the 0, 0 or any matching indice cancels, so we like that. Here we get a matching pair of dx, ux, dy, uy, dz, uz, but we can factor out the c gamma, and so we do that, and then we consolidate down to, well, this part leads us to a gamma c d dot u. If we do this to the electromagnetic field tensor, again, the 0 part or the matching indices cancel to 0, and we're left with something similar, except we have a gamma over c e dot u. So here, what we're doing by via the Minkowski force is showing that the 0th component yield these requirements. So setting them equal to each other, we get a nice little cancellation, and what we see is that d dot u is equal to epsilon e dot u, which may have been evident based on the fact that we recovered the equation from chapter 4, but now we get to see how it is with the tensor notation. So what do you think we're going to have to do with h now? We're going to have to do the same thing with both of the dual tensors. Set the 0 terms in, matching indices, run it through. You see we get another dot product, except this time we don't have a c. We just have gamma times h dot u. The dual tensor, the dual electromagnetic field tensor yields a b dot u. And as you see, the gammas cancel again, and we're left with what we might have expected anyways, which is h dot u equal 1 over mu b dot u. Again, this is for mu equals 0, so this is just the first term. Now let's see how they relate in the other cases. So now we have to do this for mu equals 1, the first spatial dimension, and this is where it's going to get hairy. So be careful how we migrate through. We see that the matching indice this time is 1, 1, not 0, 0. So here's our expansion, our summation over the news, and we see we get the components here, and we get a component, the 0th component of the 4 vector, plus another of the y components, z components, since we already have everything passed around. As you see, we have a gamma factor that's common in both, c squared from the d term, and then we have a wannabe cross product of u and h. This shouldn't scare anybody. This is kind of starting to look like a force, of course. So setting these equal with the, once we do the same thing for the electromagnetic field tensor, we get a similar form of gamma e plus u cross b. See the c squared that was in our substitution earlier. It's coming into the e, those terms that we had in one of the first slides. So it's staying consistent. This time we have a curl component for x, but of course via the Minkowski, we see what it ought to be. That being said, what we're looking like after we try to simplify these x compartment downs, the x compartment down is the extrapolation of d plus 1 over c u cross h, because we divided the c squared on both sides, but this term didn't have any c, so we put it there. This side kept its epsilon, and we're left with e plus u cross b. Okay, so we have e, u, b on the right hand side, and our other auxiliary fields on the left. So far so good, but we're going to put a star next to it since we're going to have to use it later. Okay, now we're going to do the same thing for both of the auxiliaries. We're going to have a space on this slide, so this will taper over to the next. But you see, once we plug in all the components, which I'll let you read, we end up with another cross product, except this time negative in space with these two, the d and h switched. as kind of expected. B and E switched as kind of expected. Now let's see how it simplifies down. All right. So setting these two equal via the Minkowski relations, we see that a gamma and C cancel again, no big deal. To generalize this, we get H minus U cross D, and then we push that the C term over, or excuse me, we factor that out. So here everything else is tidied up. Once we divide the gamma over, the gammas cancel. We divide the C over, hence the C squared. And then we can distribute that, which we do here, getting the 1 over C squared on the U cross E. So the goal here now is to solve this last equation for H and substitute it into star. So that's why we put it on there, so we know which equation we're referring to. Clearly here, solving this for H is just a matter of adding this term over. And then once we do that, we're gonna have to we're gonna have to algebraically sub this in, and it's going to be a mess to simplify down. But that's what we have here going on. This is the equation star, and we substituted this whole thing in. So we have a 1 over mu, we have the 1 over mu B minus 1 over C squared U cross E. That's right here. Then of course we added the U cross D term over. But now you see we have a cross product acting on this and acting on this bracket. Okay, so trying to simplify this down, well, on the right hand side, we remember that we had an epsilon equal E plus U cross B. So here then, D is equal to 1 over C. Now we distribute the cross product. So we have a triple product there, or a double cross product, so back cab might come in, or it will come in rather. And then here we have the 1 over C squared U distribution, and we still have to distribute this cross product of U cross onto B, do that there, and this onto U cross E. So we have another back cab coming in here soon. Again, it's messy, messy, and messy. The vector algebra is going to come back, and it is going to annoy you and wear you out over and over again. But that being said, let's apply the back cabs. We see we get the dot products in there now. More dot products in there. And again, we see that the right-hand side remains unchanged. And now we have to go through our final round of simplifications, and let's see what we get. That being said, we saw that we ended up with some nice cancellations, of course, and some potential easy substitutions to do. That being said, we tried getting everything to the right-hand side that we could as far as cross products are concerned. So we got U cross B over there. We got the U cross E over there, since we're trying to get U, B, and E to one side. We're going to have to do some factoring on this U squared C squared D. And then we could do add this, or rather minus this part over as well. Simply just to get everything on the right side and solve for D. So once we do that, let the algebra ring through. We see we can try to manipulate things to the best of our ability, but it's just not going to work out in a nice compact manner. So we have epsilon over C squared with the minus sign, since we move this over to that side of the right-hand equation, or to the equal sign. Then, of course, we have our epsilon branch from here, the minus from the U cross B, and then the back cab rule here. So what a cluster, of course. What was nice about this is that we see we have a 1 over U squared over a U squared C squared. So I think we can kind of understand that we're going to get a gamma here, a gamma situation running in. The only thing that we have in common as far as like the relative e's that we could pull out is we have a 1 minus U squared over epsilon mu C to the 4th E, a 1 over C squared for the dot products of E and U. U cross B, we could factor out some common factors here after distribution. And so if we're going to make some substitutions here, just to tidy these brackets down, well, of course, we'll let gamma be its normal thing, but we'll let V, normally the speed of light was 1 over square root epsilon naught mu naught. Here, since we don't know what those relativistic quantities are, we're just using V for generalized speed. So, but again, gamma is with the ordinary velocity U. So D is compacted down to gamma squared, which comes from this parenthesis here, epsilon, which we factored out of everything, period. And then we see that we have 1 minus u squared v squared over c to the 4th times e. Then we have a 1 minus v squared c squared, which can't be gamma since that's not u, the ordinary velocity. And then we see that we have u cross b minus 1 over c, and then e dot u. So that was a gigantic mess. But notice that we could have also gone the other way and solved star for D and sub that into the dual matrix relationships and gotten a similar result, which again we do. This time E and B kind of switch spots, so we see the symmetry there. And we kind of have to work around the fact that we have inverse as far as epsilon and mu and how that's concerned. But we get gamma squared over mu instead of gamma squared times epsilon. And then you see this relationship boils down to 1. And then we have a split on this. So it's actually really cool to see how these things keep their same architecture, even in different contexts. But yeah, what a mess. And I'm glad this is over, although the results are illuminating. So yeah, we only got a few more left, so enjoy it while it's here.